Hello everyone, thanks for coming. Today we are going to do a review of our week 13 lectures. In this week, we talk about parametric surface and surface integral. Parametric surface is a surface parameterized by two parameters, which we denote by u and v. The equation is r equals to x uvi plus y uvj plus z uvk. As a special case, we can get a parametric surface by rotating a curve in the xy plane about the x-axis. Suppose we have y equals to fx. If we rotate it about the x-axis, then we get x equals to x, y equals to fx cosine theta, and z equals to fx sine theta. It is relatively easy to get the tangent plane of a parametric surface. Suppose we have a point P0, U0, V0 on the surface, then the equation of the tangent plane that passes through the point P0 is P minus P0 dot partial r partial u cross partial r partial v equals to 0. P is setting point on the surface. Partial r partial u cross partial r partial v is the normal vector of the tangent plane. Next, we introduce the surface area of parametric surface. Suppose we perturb u and v a little bit, then the infinite small surface area unit is the norm of the cross product of partial r partial u and partial r partial v times du dv. In this sense, we define the surface area of a parametric surface as the integration over u and v, the domain of u and v, the norm of the cross product partial r partial u cross partial r partial v. Specifically, if we have the graph of a function z equals to fxy, the surface area of this graph is integrating over d square root of x squared plus fy squared plus 1. For the parametric surface, we can also define the surface integral. The surface integral is defined as a limit of the value of the three-variable function f at a point Pij star. Pij star is on a surface, is on the infinite small unit Sij. The value of the function times the area of the infinite small surface Sij. The formula is integrating on the surface fxyz ds, which is integrating over the domain of the two parameters d, f, r, u, v times the norm, times the area of the infinite small surface ds, which is the norm of Ru cross Rv dA. Specifically, if we have a graph z equals to fxy, then we can simplify the formula for the surface integral, which is integrating on dfxy gxy square root of gx squared plus gy squared plus 1. We can also define surface integral for vector fields. First, we can define the unit normal vector that is perpendicular to the surface, and which is Ru cross Rv divided by the norm of Ru cross Rv. For a surface which encloses an area, we can define the orientation. The positive orientation is the one for which the normal vector points outward from the region enclosed by the surface. So if f is a continuous vector field defined on an oriented surface, so the oriented surface means that we can define the positive orientation for the surface with a unit normal vector and possibly pointing outwards, then the surface integral of f over s is defined as the integration of the inner product of f and the normal vector n ds. ds is actually the norm of Ru cross Rv dA, the infinite small area. Thanks for listening.